Good day, ladies and gentlemen. You are all welcome to CMEN405 lecture number 7, Digital Electronics 2. In this lecture, we are going to look at what we call programmable logic devices. And for us to understand what these devices are, we need to know that the logic devices in general, they are divided into two types. The first one is called the fixed logic devices, and these fixed logic devices, they are nothing but these gates we use to implement any Boolean function, and they are in such a way that the moment you use them to design, they are there permanently. And the other class is what we call programmable logic devices, and these programmable logic devices, they are the ones that are generally fabricated or developed without intention for them to implement a particular Boolean function. Meaning, you can buy a programmable logic device and use it to implement different types of Boolean functions. And this programming of the logic devices is depending on what you require to do at a particular time. Therefore, they are diversified, they are not fixed. You can implement different things depending on your requirements. And these programmable logic devices also, they are of two classes with respect to whether you, the user, you are the one that will program it according to your wish, or it should be programmed by the industry according to the table or the Boolean function you give them you want to implement. So the first one is called mask programmable device, and they are the ones that are programmed in the industries based on your table of Boolean function you want to implement. If you give it to the industry, they are the ones that will program it for you. And the second class is called the field programmable device. They are the ones that you, the user, you have the flexibility, you have the right to program them yourself. Now, these programmable devices, they are of different types, but the ones we are going to discuss in this our lecture is called programmable logic arrays, PLAs. And these programmable logic arrays, they are in the class of a field programmable devices. That is, the devices that you, the designer, the programmer, you can implement any logic function you want according to the program you have written. And basically, these programmable logic arrays, they are made using two logic levels. The level number one, we call it AND level, and the other level is called the OR level. And these levels, you can call them planes. That is AND plane and OR plane. And the size of each of these programmable logic arrays is defined by the number of inputs you are going to implement. That's the function. How many variables does it have? And also the number of product terms that you want to have in that your logic, and of course the number of sums, that is the different number of functions you have. If you have two functions, it means your OR levels, they should be 2, the sum level should be 2. And as usual, if you look at this diagram, this terminal stands for my inputs, my n inputs. They can be any number. One thing we need to recognize or to understand here is the fact that each of the inputs, we have its real value, and we pass it through an inverter to get its complement value throughout. And this level of the inputs, they are first delivered to our key product terms, that is the AND gate plane. And these AND gate planes, they are connected to the M sum terms, which are the OR gate planes. And you can see between them we have fuses that you can leave intact if you need signal, high signal there, or you can break if you need a low signal. And the output of this sum level is now delivered to the output using direct connections and inverters, because sometimes we need inverted output depending on what we use for implementing initially. And as we usually do, we are going to look at the examples that will make it very clear for us to understand the explanation. The example number 1 says a combinational logic is defined by the following functions: f1, which is a function of ABC, and the mean terms include 4, 5, and 7. f2, the same function of ABC with 3, 5, and 7 as the mean terms. And we are instructed to implement the digital circuit with PLA, that is programmable logic array. And we are told that the input should be 3, of course. Our variables are 3, A, B, and C. And we are now given a restriction that our product terms should be 3 and our output should be 2. Yes, the outputs are already 2 because I have two functions, f1 and f2. So for me to solve this problem, the first thing I will do is to take my f1 and f2 and write them as the sum of my mean terms. You know, that my 4, 5, and 7 is equivalent to A, B prime, C prime, and 5 is equivalent to A, B prime, C, and 7 is equivalent to A, B, C. Same thing to f2. Now, after doing this, the next thing we'll do is to come and draw Kano maps to simplify our functions f1 and f2. And while doing that, you have to simplify f1 and the complement of the f1, the same thing to f2 and its own complement. So these are things that we know. We don't need to say anything about this. We have looked at them severally. And this is the Kano map for simplification of my f1, and this is what I got. And this is the one for implementing or simplifying the complement of f1, and this is what we got. The same thing for f2 and its complement. Now, the next thing I will do is to say, okay, the two functions given to me are A and B. Now, if you look at A, I have two product terms, that is AB prime and AC. And if you look at C, I have AC and BC. Now, I am asked to use only 3 product terms. Now, comparing these two, you can see that this AC belongs to f1 and it belongs to f2. Therefore, we can eliminate 1, meaning the product terms should be 1, 2, and 3. This one should not be repeated. So if that's the case, it means the condition we are given to use only 3 product terms is satisfied now. So I'm going to make my implementation using f1 and the f2, the real values. Now, the next thing I will do is to draw what we call program table. In this program table, as you can see, the first column, we write the product terms we have obtained from our Kano map simplification. You can see from here I have AB prime, I have AC, and then I have BC because I will not repeat AC. So look at them, AB prime, AC, and BC. The second column is for the numbering the product terms. You know, this is number 1, this is number 2, and this is number 3. Now, the next column should be divided into 3 for my 3 variables A, B, and C. Now, this is A, this is B, this is C. And if you look at this product term, it has A, so under A I put 1. It has B prime, under B I put 0, but C does not exist, I put dash. If you look at this, A is there, I put 1 under A. There is no B, I put dash here. And I have C, I put 1, the same thing for this. Now, the next thing I will do is to come to the fourth column, which is divided into 2, f1 and f2. Had it been I have 3 functions, I'll have 3 divisions, f1, f2, and f3. Now, I'll see this term AB prime. Is it belonging to f1? Yes. If we go back here, you see that it belongs to f1 only. f2 does not have it. So, under f1 I put 1, under f2 I put dash. But this AC is the common term that belongs to f1 and f2, so I put 1, 1 under the f1 and f2, and the last one BC is belonging to f2 alone, so under f1 I put dash, and under f2 I put 1. Now, the last thing I will do is to come here and say, okay, I am doing this my implementation using the real value of f1 and real value of f2, not their complements. So that is why under this T/C I put TT, meaning I'm using the true value. Had it been I'm using complement of any, I'll put C in that place. Now, after doing this, the next thing and the last step of the solution is to draw the logic diagram. And for us to draw it simply, we use the single line diagram we have been discussing previously in other lectures. So I say this is A, this is B, and this is C. I draw a horizontal line, vertical line going down for A, and I pass it through an inverter, another line going down to give me A prime. Then I do the same thing for B, I do the same thing for C. And from my program table, I know that I have 3 products, and these 3 products, they will be represented by 3 AND gates. Then, excuse me, I know that the functions given to me are 2, F1 and F2, so I have 2 OR gates with their lines going vertically downwards. Now, the first one, if you look at it, my first product term is A and B prime. So I'll come to where A is and put this mark, meaning I have a connection. Then I'll go to where my B prime is and put a connection, which means the output of this AND gate should be AB prime. For the next one, AC, I'll put here and here, which means I have AC. For the last one, B and C, I put here and here, and this is. Now, as we know from the simplification we have made, we know that this AB prime and AC, they belongs to F1. So I cross here and cross here, which means they have connection to F1. And I am using the actual value of my F1, therefore this one should be connected. As you are seeing here, definitely there is a mistake. Here should not be connected. I should have a connection here. Okay, I should have a connection here, which means I'm implementing with real F1. So if you go to the program table, you also know that AC and BC belongs to F2 again. Now I will make connection here and here to F2, and the output of this F2, I'm supposed to have this one intact and this one broken, because I am implementing using real value of F2. Please, this one and this one should not be connected. This one and this one should instead be connected, please. So if we understand this, this is all we need to do in order to implement any Boolean or set of Boolean functions given using PLAs. We go to the second example for better understanding. And this example also gives us 2 functions, F1 and F2, with their mean terms, and we are asked to implement them using 3 input, of course 3 input, because I have only A, B, and C. For product terms, this is only my restriction, and 2 output, of course, F1 and F2. Now, in the solution, these are my mean terms, and the next thing I will do is to simplify my F1 and F1 prime, F2 and F2 prime, as I did in the previous example. And these are the things I got. Now, I am asked to limit myself to only 4 product terms. Now, let me look at this and say, okay, here for F1, I have AB, AC, and BC. And for this one, I have A prime, C prime, B prime, C prime, and ABC. Now, comparing these two, you know that there is no a single product term that is common for the F1 and F2, which means if I am to take the real F1 and F2, I must use 1, 2, 3 plus 1, 2, 3, 6. That is contrary to the condition given to me. Now the next thing I will do is to compare the real F1 and the F2 prime. And looking at the two also, they don't have anything in common. So the next and the last option is to compare F2 and F1 prime. And if you look at it here, I have A prime, C prime, look at it here. And also if you look at this, I have B prime, C prime, look at it here. So it means here I have 3, here I have 3, 6, but 2 are repeated. So when I eliminated the 2, I will be left with only 4 product terms. So I move ahead to draw my program table. First column for the product terms, second column for their numbers, the third column for the input A, B, and C, and there we have 3 divisions for the 3, and the last column for my outputs, which are the functions F1 and F2. And as I did, I will say, okay, here I have A prime, B prime. Under A I put 0, under B I put 0, but C is not here, I put dash. Here I have A prime, C prime, under A 0, there is no B, dash, C is 0, up to the last one. And you can remember that I use the complemented value for F1 and I use the real value for F2. That's why here I have C for complemented value, T for the true value. And the next thing is to use this my program table to implement the logic circuits. And as you can see, these are my three variables, A, B, and C. Each one pass and through an inverter to give me their complements. And I draw 4 AND gates, look at them, to cross these ones horizontally, and I draw 2 OR gates to cross these ones vertically. Now, going back to my implementation or program table, I have A prime, B prime. So here I have connection for A prime and B prime to present this. The next one I have A prime, C prime, and the next one I have B prime, C prime. The last one I have A, B, and C, the real values, and here should be ABC, please. Here should be ABC, not BC. There is A missing. Good. So after doing this, the next thing we'll do is to say, okay, these 4 product terms, where are they belonging to? You can see that the first 3, they belongs to F1. That is this one and this one and this one, all of them belongs to F1. So I make connection here, and another connection here for the 3 belonging to this F1. And you know, I make my implementation using the complement of what? F1. So therefore, this inverter output should be connected, because we need to complement it again so that we can get the true value of F1. But as you can see, I did not make the connection. There's a mistake here. This should be connected and this should be broken. Then finally for F2, this function, this one, and this, the 3 of them, that's starting from the second to the 4th, they belongs to F2. And for this, I make my connections, look at them, here, here, and here. And in this case, my F2, going back to my table, I am using the truth value. So therefore, this output here should be connected, and my complemented value, that's the output of the inverter, should be broken. Okay, so therefore correct these ones, please. Don't say that I'm the one that did it. They are mistakes, therefore correct them. So ladies and gentlemen, this is all we have here. And before we go, I would like to encourage you to try doing this assignments. I don't want to call it assignment because I don't give assignments. I don't like it most of the times because students just copy from one another. But use this one as your homework and try to refresh your understanding. And of course, if you wish, if you have any problem concerning the assignments or any other thing I discuss in this lecture, you are free to contact me. Thank you very much. And this is the end of this lecture and the end of the course. Thank you very much.